A year ago, somewhere in this building, Brandon Rhodes gave his speech about classical design patterns. Where are they now? How many of you saw this presentation? Oh, great, quite a lot of you. So, for those who didn't, he stated that the problems that those classical design patterns from the book by Gang of Four are in some percentage already solved, and some of those patterns are already implemented in present languages, and that's why we cannot see use cases of those design patterns or those design patterns in present code. And I had similar feeling when I was learning Solid in JavaScript, that I couldn't see those most vital use cases of Solid. So what happened to Solid? Did JavaScript somehow solve the problem that Solid addressed? Well, not at all, because I saw ugly violations of Solid principles in JavaScript. I saw database details, API database details, leaking to all the code of the back-end part of the application. I saw functions that grew large and were not maintainable, not reusable, and bugs. Bugs that may have been avoided if people stuck to Solid, or if perhaps people knew Solid, because when you don't experience the instant karma of violating Solid principles, perhaps you don't have to know those Solid principles at all. And I think that it may be a bit like a time bomb. And that's the reason for this presentation. I would like to make attempt to translate Solid into not Solid-like languages. For whom I prepared this presentation? For people who are either new to Solid or, like me, they cannot find those important use cases of Solid principles in their daily work. So they work with, I would state, non-Solid-like languages. However, if you are a more experienced developer with extensive knowledge and understanding of Solid, and I'm afraid that I may not exactly meet your requirements, of course you are very welcome to stay. We will talk about what is Solid in details with explanation and examples in JavaScript. If you don't know JavaScript, that's okay, because you'll probably understand my examples. I feel that they may be international. We will try to define what are Solid, non-Solid-like languages, what is this key difference between them, and then we will go to a powerful conclusion that I was trying to prepare, and I challenge you to stay and listen how I perform with this conclusion. We know Solid for decades now. There were in books, magazines, in mathematician theories from even 19th century, but we wouldn't be sticking to Solid principles, talking about it, if it wasn't for this man here, Robert Martin, so-called Uncle Bob. He was the one to take everything together and to advertise it and teach us about it in his Clean Code series, which I recommend. Solid stands for single responsibility, open-close principle, list of substitution principle, interface segregation, and dependency inversion principles. We know when you read about single responsibility principle in the internet, you may encounter a statement that it's about a class doing exactly one thing. How many of you would state that class should do exactly one thing? Oh, 1 person, 2 person, 3 person. You know, in my understanding, the class does one thing, but it has single method. If it has more methods, it does more things. And it should do more things. It should have at least more methods. And it's not about a class or software entity doing one thing. It's more about a single reason to change. And this reason is a person who would like this piece of code to be changed. Let's put it in other words. There should be only one person in entire organization that wants some piece of code to be changed. Perhaps some examples. How many of you like rebases? Those complicated ones with a lot of conflicts. No, oh, there's one person. Well, we are different and it's okay. But most of you don't like I start liking you because we are the same. I don't like them either. Suppose there is an HR department in some company and accountants department. And because of do not repeat yourself rule, they share the common module working hours. And both departments would like to have a change to this module at the same time. Of course, those developers will meet in a rebase with many conflicts. The same company sells parts to individual customers and enterprise customers. The enterprise feature is already there, and let's say that I was asked to deliver this individual customer's feature. So what I do, I went through the code base to find code that I may reuse, and I found it, a get basic price module. There is some function that gets basic price, and I import it directly to my feature. And what may happen now? My friend may change this feature because he doesn't know that I imported it from his folder. And we have a problem because how many of you do test-driven development at your work? There are a few people. I was just curious. But not everybody. And this is just some simple logic. So no test for this. We'll discover this problem when it's already too late. So how could we prevent this? In my team, we have such a solution that there is a function folder. It's some above in the hierarchy. And this module might have been promoted to this function folder. And there are rules regarding function folder. This is reusable code, so it should be well tested. There should be only a single export from the file. And no one is allowed to change semantic of the code that's already in exported functions. And it should work. There is another solution, perhaps not the best one, but it's still acceptable, that we may do a copy of this module for my feature. But isn't this violation of do not repeat yourself rule? Well, do not repeat yourself rule is about the code that would change for the same reason. And this code changes for two different reasons. And that's why it's still acceptable. It's not the violation of do not repeat yourself, but perhaps this function is a bit better. Sticking to single responsibility rule means less conflicts doing rebases, fewer bugs, and better maintainability. We know open cross principle thanks to Bertrand Meyer. He said that our software should be open for extensions, but closed for modifications. I guess that it's already understood, so let's jump to examples. A decorative pattern was something that allows you to modify, add functionalities to your code without modifying it. It was generally designed for classes, but let's do it for functions. You will discover that it's a very basic thing and a very fancy word to do this. So we have a function that fetches something from an external API, and let's add logging functionality to this. It's a perfect modification, isn't it? There is a isVerbose flag, and by default it's false, so we don't have to word through all the code to do changes there. We can just set it to true when we need logging. So why is the sad face here? How many of you can spot single responsibility violation here? Well, not many people. There are two responsibilities in this class. One is logging. So one person in our organization may want to change the logging, text functionality or whatever, and some other person may want to change this API, for instance. So we already violated one principle. And we could do this like that. So it's just wrapped in a function. We are calling a function from within a function. And as I told you, it's a very fancy word, this decorator pattern here, to do basic stuff. It was said that data structures should be over control. Data structures are said to be easier to debug. And this is a function, so this is control, this is some logic hidden in a function. Of course, it's very simple. Some car dealer company, even a non-programmer could add new sedan here, but still the face is sad because we would violate open cross principle. Perhaps it's not tragic in this case. Of course, I already saw huge switch case functions, but it may be done like this. There is a data structure and a function that wouldn't have reason to change probably. And such data structure may be even saved in a database. These functions may be stringified and then resurrected with eval function. And eval doesn't have to be evil because you trust your database, don't you? So when you violate open close principle, then your code stops being reusable. It becomes too large. You may cause bugs caused by not exactly understanding the whole legacy code. And open close principle violation often hides violation of other principles. And among all, I believe that one of most important ones is Liskov substitution principle. It may be a bit tricky to understand for people who are new to this. That's why I'm not going to read what Barbara says here. It's a bit complicated. Instead, I will show you my own example. There is a user U, and this user U uses type T. Subtype S is the subtype of T if this user cannot tell the difference. Now this car example. User U is a driver, and he drives the blue car. Now they take away the blue car from him, and they give the white car to him. Will he notice the difference? Probably not, because he's a very careful driver and he will not notice the difference. He never overspeeds. But if he was a race driver, he would never want to change 300 horsepower to just 50 horsepower. So in this case, this wouldn't be the subtype. Please raise your hand if you think that a square is a subtype of a rectangle. Okay, a few hands. And you're right, because at mathematics they taught us that it is the case. The square is a subtype of a rectangle. However, let's take a look at this example. A square has two sides, whereas the rectangle has height and width. And the user of a square may expect that if we set side of the one side to 3, the other side will also be 3. And it's not the case for the rectangle. And there is this area problem. If we set side of the square to 3, the square user may expect that its area will be 9. And it's not, it's not the case with the rectangle. And this is a behavioral problem. You cannot discover these expectations by a square user with TypeScript and other static code analyzers. And it's good to remember this. If you analyze this problem more deeply, you will understand that neither square is a subtype of a rectangle, nor rectangle is a subtype of square, at least in representation. Let's draw some squares and rectangles. Here are squares and rectangles in one list, and you would like to draw them with a draw rectangle, then with a draw square method. And if you do this, this is the browser's Canvas API, you'll notice that when you draw squares, rectangles will not show on the screen, and there will be no errors. And now please analyze when you have 1,000 figures that just one is missing. Let's correct this function, shall we? There is an if statement and it will work. At least for now, because we violated open close principle. And of course, Liskov is only hidden, it's not corrected. We don't know where this code will go in the future, how it will evolve. And it may lead to the point where this will cause some disaster. Type mismatch may also be some kind of Liskov substitution violation. In JavaScript, let's say we have numbers, and we expect this list to have numbers. But wait, quoted O sneaked in here, and this is a string. JavaScript will convert this to string, and we will get string 301 instead of 4. We can still discover it because this is a string and it should be a number. But if we subtracted something from the number that is stringified, then it will be converted back to number in JavaScript. And now it's better hidden. we may not see such a problem instantly. And refused bequest. Suppose we have a company that makes software for schools and it serves school attendance. But now we would like to extend this functionality for preschoolers. So we delete this grades object. It's not needed here because in Poland preschoolers don't get grades. And it should work. But let's prepare a statement about a person. And this statement has getAverageGrades function, and it accepts grades. And in this case, grades will be undefined, so we will get a refused bequest error. Okay, now let's hide this problem. This is the ternary operator. It's a conditional statement, so we did the same thing. We violated open-close principle, and we tried to hide list of substitution violation. And we don't know where this code will go in the future, and that's the reason we may have problems. If we would like to stick to list of substitution principle, we may use static code analyzers, for example, TypeScript, maybe one of such solutions, but it will not discover behavioral problems like I show you with square and its area. We may use test-driven development, it may help, or design by contract. There is preconditions, so before we launch a function, we should calculate preconditions and see if they are met. Then we can run a function. And after we run the function, post-conditions should be checked if we shouldn't handle some error path. We know interface segregation principle thanks to this guy again. He said that we shouldn't depend on the things we don't need. And he said that while he was working in Xerox, there was a complicated copy printer. Soft was in C++, and it would compile in an hour. Now imagine, you do a tiny little bit change to the code, and you wait for an hour, not 2 minutes, like Pavel said, a speech before, but an hour. And by getting rid of all dependencies, they reduced the time to just 2 minutes. And this is a case that we will not experience in JavaScript. That's perfectly hidden from us. And this is this instant karma. We just violate something and we got long compilation times, really long compilation times. But still, let's look for some use cases of this principle, shall we? I called this deep dependency. We would like to test a function, and this function calculates a mean of a number, some numbers, and multiplies it by some factor. And it uses a function from second module, getMean. And this getMean uses some getSum function from some other module. And this first root of all dependencies here has not needed function. This is an asynchronous function, by the way. And it's not imported anywhere in our example. So it's not imported here, nor it's imported here. And there is a test. We expect it to return 55, and it fails because we have some regenerator runtime problem. And what's regenerator runtime? We did not import any async here. So what does it do? It allows us to use async await keywords in legacy versions of JS. And please notice that we did not import this asynchronous function anywhere, and we just import something else. And it didn't prevent this code from being executed. So if we have something that may be executed, we import something from a module, some side effects that may to happen, they will happen, and this may cause problems. Now we have cycle dependencies. Of course, this would be horrible in solid-like languages, but we just import something from modules in a circle, like here. So they depend on each other in a circle. And such code may work in JavaScript. I solved violations of this. They were quite difficult to fix because there were like 15 modules depending somehow on each other, and it was some legacy code, quite difficult to fix. But it may cause problems. Long compilations, like in TypeScript, we still compile. Infinite loops, unaffected behavior, problems with debugging and testing. We may fight it with static code analyzers like slint. It will show us problems in every single module where we violated this. Or we may pay attention to errors and warnings, but still, as I told you, when we have 15 dependencies in a circle like this, it may be difficult to break. So for our team, a proper dependency structure works. I already told you about the functions folder with its rules. So single export, no semantic changes, well tested, and there is some other rule I already told you about. Don't import anything from neighbor features. And I don't mean neighbor folders, but neighbor features. So this is a dependency of features. If two features may be independently deployed, then they are independent. And when you have to make one feature and then another, they depend on each other. And you shouldn't import anything from children in this structure here. This is what works for us, at least. The conclusion from dependency inversion is, not dependency inversion, sorry, interface segregation principle is that code in every module that is imported is executed, so side effects happen. Dependency inversion is something that we know thanks to, again, Robert Martin. He said that we shouldn't depend on the details. And what are details? I already told you about database, that it is a detail. We may want to switch from SQL to non-SQL database to a file system to some external API, and application shouldn't know about what we are using because the code will be difficult to modify. And this is something that should work in JavaScript, in Node.js. We have DB operations. This may be a whole folder with different modules or a single module, and only this is allowed to speak to database or its API. This database API knowledge may not leak into structures of a program because it is a detail, and in such case, modifications will be quite difficult. Still, everything depends on DB operations in non-solid-like language, so every single module from here knows about DB operations somehow because there is this chain of dependencies, and it would be a disaster in solid-like language, because in this case, if we would like to modify something in these DB operations, everything would have to be recompiled and redeployed, and many teams will be involved in this. That's why they use some interfaces, and these are other interfaces than in TypeScript. And this just separates those dependencies, so this DB operation may become a plugin, an easily switchable file. We will never witness this behavior in JavaScript, but still let's look for some use cases of dependency inversion. No knowledge about wrapped element. There is so-called modal in graphical user interface design. It just hides something that's in the background. You cannot play tic-tac-toe in this example. You may only interact with this window and read about tic-tac-toe. Then you have to close it before you continue. And there may be one modal component like this in React, let's say, because it doesn't have to know what it displays. It doesn't know what the children is here. And there is a high order function. This is an adapter pattern. The adapter is something like, if I meet a Chinese person and I talk to Chinese person, we will not understand each other because we don't know languages. So either one of us has to change themselves. So let's say I will have to learn Chinese and then I change myself, but it's quite expensive for me. So it's better to hire a translator, and this translator is like an adapter. And when two interfaces want to talk to each other, they may need this adapter to do the translation. And functions, of course, also have interfaces, like this reduce function here. It's an array method, and it just reduces the whole array to just a single value. And part of its API is a callback function. This callback has accumulated and item. Let's say accumulated is a value calculated so far, and item is something we are working on currently. And we shouldn't change reduce function as it's built in. And now we would like to calculate circumferences of rectangle and add them all together. So these are the rectangles, and this is the formula for circumference of rectangle. This is the function that would be accepted by reduce function. And this is the reduce function usage, and it will return sum of all circumference of those rectangles. And of course, there is too much knowledge here because this function knows that it calculates something for rectangle and that it calculates circumference. So it knows already two things. And we may solve this way. So there is the higher order function that accepts this implementation detail, and then it returns a function that already knows what it should. In this way, this code becomes more reusable, and it should work. Again, the same example I already showed you about those switch statements, that this is the whole structure of a problem, and we may decouple it from the function. So the high policy should be independent from the low level. If we violate dependency inversion principle in solid-like languages, this will be a real disaster. Many people will be angry because they will not be able to compile, to deploy. And this is not the case in non-solid-like languages. However, our code becomes difficult to change, and it will have to be changed in many places at the same time. We'll have many code repetitions, and examples where we will not violate this principle is that hopefully we are not going to import anything from our tests, and our libraries will never import anything from us. So, important thing about those non-solid-like languages that the code there is quite easy to be changed. And by the way, JavaScript is not designed for very huge applications, and the rest is not that important. And as for solid-like languages, they compile, they don't run in an interpreter, and change to a single file may be a bit difficult to do because of all recompilations, redeployments, retesting, and they are meant for bigger applications. So we have 10 gigabytes, many teams do something at the same time. They want to work independently, and they may work independently thanks to plugins, so easily switchable files. And they will work, they will be easily switchable as long as we stick to solid. And this is not relevant. So this key difference that I found that it works for me, for my team, is that non-solid-like languages are more easy to be changed. And now I admire you because you stayed until the powerful conclusion. I would like you to close your eyes and imagine one thing. Please imagine that you work for a car company and that you produce software for cars. And you finish your job, you go back home, there's a weekend, you are with your family and friends, and everything is fine. But after a few weeks, a bad information comes to you that there are accidents. People die because of your software, because you violated list of substitution principle. And you write in non-solid-like languages, so you didn't even know that you violated it. And now I would like you to imagine the same scene, but some other things will happen. So you work for the same car company, you write software, and you probably did not violate list of substitution principle because you already did your homework. Once you were in a situation that you couldn't go back home for a weekend. You had plans. Your family is angry, friends are angry, your coworkers are angry because you violated solid principles, and you cannot go back home. You have to fix your bugs. And because of this, you become an expert with solid principles, and probably you will not have this fatal accident case. Where you would rather be, in the first group or a second group of people? Please don't tell me I believe that in the second group of people there are no murderers or lazy developers here. However, if somebody writes in a non-solid-like languages, there is a possibility that that person does not have knowledge about solid. And this may be harmful in some situations. So if you would like to have your conscience clean, then please keep it in mind that only one person in the whole organization should want your code to be changed. You shouldn't modify your code. Instead, you should extend it. You should think about the types. You shouldn't depend on the things you don't need. And you shouldn't depend on the details. I wonder how I managed to finish it before time. Thank you very much. It's everything I prepared for you, unless there are any questions. Are there any questions? There is one question there.
Could you define what is a solid-like language for you?
Well, this is a language where it's easier to spot those hidden cases. So when you change something to the code, there will be they may be long compilations if you violate solid principles. So in this case, solid principles was designed for languages like C++, C#, Java, and those languages compile to some TypeScript compiles to JavaScript, and those generally compile more to a machine language. Change to a single file may cause need of recompilation and redeployment of everything. They may be used in bigger applications. They are plugin architectures, so there are easily switchable files. They are strongly typed and object-oriented, whereas non-solid-like languages, for me, have more easy to change modules, may run in an interpreter. JavaScript was not designed for bigger applications. And there may be compilations, but this is not that relevant.
My question was wrong. I was thinking more about explanation of properties of the language, not of use cases.
Well, I defined it by the use cases.
Yes, yeah.
Because when you don't see those use cases, you don't see this. When you change something, you violate dependency inversion principle or interface segregation principle, and you don't get this instant karma, then this is a non-solid-like language. At least for me, it's not some definition. It's just a term for this presentation.
Yeah. Mm-hmm.
Okay.
Thank you. Yes.
Thank you very much for the question. Are there any more questions? Well, if there are no questions, I believe that you'll just have a longer break. Thank you very much.